Welcome to The Explainer. Today we're tackling something absolutely mind-bending. It literally challenges the very foundation of how we understand math, and, honestly, reality itself. We're exploring Zarif Mohammed's working research manuscript from August 2026. It's called Beyond the Number Line, a polyaxial and recursive model of numerical structure. In it, Mohammed formalizes what is known as the ADI framework, and it completely reimagines the numerical space we actually inhabit. So, get ready to stretch those conceptual muscles a bit.
Okay, let's dive into this. I want you to picture the standard number line you learned about back in grade school. You know the one. It's a flat, one-dimensional line stretching perfectly from negative infinity right through zero, all the way out to positive infinity. It feels absolute, doesn't it? Well, Mohammed's manuscript asks a really profound question. What if that familiar line isn't the absolute truth of our numerical universe, but kind of just a shadow? What if it's really just a low-resolution, one-dimensional projection of a much larger, infinitely more complex reality?
To really wrap our heads around this, let's frame our journey by comparing two totally distinct mathematical worlds. On one side, we've got our standard number line. It's an exact one-dimensional Archimedean ordered field. And hey, Archimedean basically just means there's no such thing as a number strictly smaller than all positive fractions. In this standard world, infinity is just a conceptual endpoint, right? It's a boundary symbol you can never actually reach. But on the flip side, we have the ADI polyaxial universe. Here, numerical space is multidimensional, it's recursive, and it totally blows the roof off our standard limits. It features distinct, actually calculable levels of 0 and infinity. It acts as this massive carrier space, and our reality, well, it might simply be a tiny cross-section of it.
Section 1. Zooming in. Levels of 0. All right, to really grasp this, we need to completely shift our perspective. We're going to look inward, microscopically inward, right at the very center of it all. To formalize these levels of 0, the manuscript introduces us to a mathematical tool called Hans series fields. Now, don't let the jargon intimidate you. Basically, you can think of a Hans series as a precise mathematical system that uses value groups to rank infinite and infinitesimal scales. So instead of just vaguely saying a number is really, really small, Hans series fields give us the precise tools and algebraic equations to calculate distinct, ordered asymptotic scales of magnitude. It literally gives us a way to bring shape and structure to the unimaginably tiny.
And what these Hans series allow Mohammed to model is the concept of valuation shells. See, in the ADI model, 0 is not a single terminal point. It's not a brick wall that you just hit and stop. Instead, the neighborhood of 0 is this heavily stratified hierarchy. Imagine approaching 0, but instead of reaching an end, you pass through infinite nested shells of infinitesimals. Each layer approaches 0 at completely different asymptotic orders of magnitude. And these shells, they are highly organized, by their specific valuation, by whether they're positive or negative, and even by the exact direction from which they approach 0.
Section 2. Zooming out. Polyaxial infinities.
So if that's what happens when we zoom infinitely inward, what exactly happens when we reverse course and look outward? Well, this brings us the concept of reciprocal duality. Now, what's really interesting about this is how the mathematics is constructed so that inversion maps perfectly from the center all the way to the edges. That means every single infinitesimal shell buried deep within the neighborhood of 0 has an exact corresponding infinite level expanding outward. Infinity is no longer just some vague concept or a single endpoint symbol on a graph. It is a structured hierarchy of reciprocal magnitudes. Both positive and negative infinity have distinct, nested levels.
And this right here brings us to the core of the framework, polyaxial space. Up until now, you might just be picturing zooming in and out on a straight line, right? But polyaxial space means we're operating in a numerical reality that contains multiple independent directions and degrees of freedom well beyond a single axis. We aren't just moving left and right anymore. We are expanding into entirely new sets of independent numerical orientations, like positive and negative imaginary infinities, and frankly, far beyond that.
This elegantly illustrates exactly what happens when we start adding these axes. Because adding dimensions fundamentally changes the algebraic rules of the space we exist in. Think about it. In one dimension, real numbers give us a complete ordered field. In 2 dimensions, complex numbers give us our imaginary eye. But if you push that to 4 dimensions with quaternions, you actually lose commutativity, meaning A times B no longer always equals B times A. In a general ADI algebra, the number of independent axes could be vast. And that means the rules of multiplication have to be strictly determined by very specific structural axioms.
To truly understand the sheer scale of this, let's look at the formula for coordinate signatures. 2l plus 1 all to the power of d. This represents the massive combinatorial explosion of resolved states in this system. If an observer resolves d independent directions and l levels of magnitude in each sign, the number of possible states isn't just large, it grows exponentially. It represents a vast, nearly unfathomable external numerical domain just filled with interacting dimensions and recursive scales.
Section 3. The polygonal projection principle.
So you might be wondering, if this massive polyaxial reality is out there, why do we only see a simple one-dimensional number line? Well, the crucial point to internalize here is that the standard number line you know isn't wrong. It's exactly correct within its own role. But it is essentially a lossy, low-resolution compression of a much richer carrier space. When a lower-dimensional observer looks at a higher-dimensional reality, mathematically speaking, information literally must be lost. Multiple external states get collapsed and identified as the exact same internal number. Let's walk through how this builds via the ADI projection hierarchy. You can kind of think of this as a mathematical Plato's cave, and it is truly incredible. Step 1, you have the massive external polyaxial domain. In step 2, that gets projected down to an observer space, which is constrained by whatever sensory or simulation limits happen to exist. Step 3, it's sampled by a polygonal frame, basically a finite set of resolved directions. And finally, in step 4, all of that breathtaking complexity is shaved down into a single coordinate, the internal line, a one-dimensional shadow on the cave wall.
Now, a common phrase you'll hear in the ADI community is, the number line is an n-sided polygon. The manuscript clarifies this meticulously because sides are not dimensions. Think about a hexagon. It has 6 sides, but it exists perfectly in flat, two-dimensional space. The value n, the number of sides, merely measures representational resolution. It's much like pixels on a screen. A polygonal frame acts as a cross-section of a larger reality. It's an over-complete measurement frame, not a literal replacement for the real number line.
Section 4. Shadows of a richer reality. So, what does this all mean for us, the observers trapped inside this mathematical framework? When discussing the limits of what we can actually comprehend, Mohammed draws a really strict boundary. On one hand, we have epistemic unboundedness. Basically, for any coordinate stage we can represent, we can always mathematically build a bigger one by adding a new direction or a new scale. But on the other hand, we have foundational non-totalizability. Because of how standard mathematical ZFC set theory works, you can't just casually bundle all these infinite recursive extensions into a single comprehensive set. Doing that structurally breaks the bounds of standard mathematical containment.
And that leads us to the ultimate takeaway. Up to this point, the paper has relied entirely on proven, constructible mathematics. But here is the grand ontological conjecture, that the numerical structure underlying our reality, perhaps an observer simulation, actually realizes these independent directions. Our familiar tools, our number line, our complex plane, they are strictly limited by the processing resolution of our interface with reality.
Which leaves us with this final, thrilling thought. We've seen how standard math rigorously allows for hidden dimensions, nested infinitesimals, and towers of infinity, all perfectly invisible to a one-dimensional projection. So ask yourself, if our mathematics, our very perception of magnitude and direction, is constrained by an observer resolution frame, what vast polyaxial dimensions of reality are we currently failing to see? Thank you so much for joining me on this explainer. Keep questioning the framework, and I'll catch you next time.